Now that we've discussed what electric charges are and how they apply forces to one another, it's time to start thinking about charge transfer, aka how charge moves from one place to another so that objects become charged. All macroscopic objects contain electric charges, and an object we consider to be charged if there is an imbalance of positive and negative charges, so that they do not equal one another. We say that an object will be therefore electrically neutral, or just neutral, if it does not have this imbalance of charge. So if I have some object here, some metal sphere for instance, and the number of protons, which we'll go and abbreviate here with plus Q, and number of electrons minus Q, if those are balanced, well then the total electric charge on the object would be 0. We would say it is not charged. But we can have an imbalance. If it is positively charged, it means we have more protons than electrons. And if it is negatively charged, it means we have more electrons than protons. The first thing to think about when we talk about electric charges moving is that they are transferred or redistributed. They are not created nor destroyed. They go from one place to another. They don't just pop into and out of existence. And this is largely governed by the law of conservation of charge, which appears to be one of the fundamental laws of the universe, that the net charge of a closed system is constant. Now, a couple things to keep in mind here. First off, usually it's going to be the negative charges, and specifically we're talking about the electrons, that are moved and transferred rather than the positive charges, which will typically be protons. Now, there's a couple different reasons for that. The first is that, well, if we look, for instance, pretend this is a nucleus here with protons and neutrons in it, and we have these electrons in the electron cloud, the electron orbitals outside the nucleus. Well, the electrons are much further away from the nucleus. They're much closer to the next atom, so it makes sense that it would be easier to lift them up and move them from one place to another. Additionally, as we can kind of see here, these electrons are way less massive than the protons. Now, they have the same electric charge, one being positive and one being negative, but the electrons are much, 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 much tinier, approximately 1,500 to 2,000 times tinier, and for that reason, it's a lot easier to accelerate them. Now, another thing we need to keep in mind here is that this is the net charge of a closed system is constant. So that net is really important. We actually can create and destroy charge. It happens in a variety of particle physics processes, but not very much in our day-to-day life. But even when this occurs, if I have two particles pop into existence and then destroy each other, well, they must always happen in tandem in these positive and negative pairs, so that the total charge of the system is constant. Now, in general, we have two different types of materials when it comes to charging. One of these will be electrical conductors. Now, these are materials that allow charges to easily move through them, so it's very easy to get charge from one place to another within the material. Now, typically, when we think about this, the number one example we think of is going to be metals. Metals are very good electrical conductors, and the reason for that is that if we look, for instance, this is like some piece of silver, so this would be the nuclei of the silver atoms. Silver is Ag on the periodic table. And metallic bonding forms in such a way that the electrons, particularly in the outer valence orbitals, the outer valence shells, is just shared between all of these atoms. So it's very easy for those negative electrons to go from one place to another. Now, the other side we have is insulators. So insulators are materials that do not allow charges to move easily through them. Literally just the exact opposite of conductors. Now, this is usually going to be non-metals. And why that is because non-metals typically undergo covalent bonding. When they undergo covalent bonding, for instance, like water molecules here, so I've got my oxygen and my hydrogens, and these are held together through covalent bonds, and that means the electrons are literally shared between the hydrogen and the oxygen. So it's very hard to separate them away because they're being pulled by multiple pieces of the same molecule. Now, this also goes for instance, plastics, rubber, glass, wood. Typically speaking, if it's a good thermal conductor, it's a good electrical conductor. And if it's a good thermal insulator, it's a good electrical insulator. It's not always the case, but it's a good kind of way to think about it. Now, what this tells us now, water is an example that most people get a little confused by, because you think to yourself, well, wait a second, water, you don't want to be in water when electricity is around, and that's because water is actually a very good insulator. It's hard to get charges moving from these water molecules, but we can dissolve salts and any sort of impurities in this water, and then you would have kind of like an electrolytic solution where you would have basically positive and negative charges flowing around, and that is when it can be very dangerous. So if you have pure water, pretty good insulator. Any sort of dissolved something in it can be much more of a conductor. So how do we transfer charge from one place to another? And there are actually pretty much 3 ways to go about doing it. The first one is pretty straightforward. You basically just rub 2 objects against each other. And when we do that, electrons can be stripped from one material to another material through a combination of adhesion and friction. There's a lot of little small molecular force things happening there. And this is often called the triboelectric effect, because tribo means rubbing. That's what that stands for. So kind of like the rubbing electric effect. Now, what determines whether or not a specific material is going to attract electrons or want to get rid of electrons? Well, there is something called a triboelectric series. Frankly, it's not fully understood why materials go about it in quite this way, but up at the top here, these are going to be materials that want to get rid of electrons, and down at the bottom we have materials that want electrons. They're going to be more likely to attract electrons. So imagine we have, for instance, a rubber balloon and a piece of wool. Well, rubber is going to be down here. It's going to attract electrons, and the wool is up here on the positive, and it's going to want to get rid of electrons. So initially, they are both neutral. They both have an even balance of protons and electrons. We rub the balloon against the wool. You rub it vigorously back and forth, and when you do that, you literally strip electrons from the wool to the balloon, so that now, where I originally had 2 neutral objects, I now have a negatively charged object and a positively charged object. The next way to transfer charge is through electrical conduction. Now, if you remember back to thermal conduction, that was when we had objects touching each other, solids particularly, that could transfer heat between them. Electrical conduction is much the same thing. This is a transfer of electrons from one object to another through contact. So, for instance, imagine I have a negatively charged sphere and a neutral sphere, and if they come into contact with each other, well, the negatives on a negatively charged sphere are going to want to get away from the really big concentration of negatives around them. They're going to go to the other sphere. And we're going to end up, when we separate them now, having a new negatively charged object, and the negative charge of this original object will have gone down. Let's go ahead and look at the other way. Let's say that this object on the left is positively charged, and one on the right is neutral. They touch. Remember, it's negatives that typically move, so negatives are going to move from the object on the right to the object on the left because they're attracted to all those positives. We separate them, and now we actually have 2 positively charged objects. We have the original positively charged object, though the positive charge will be less because there are more negatives on it now, and then the rest of the positive charge will now be on this other object. So the important thing here is that the net charge of the system must still be conserved. So originally, we had no charge and a negative charge. So if these spheres are identical, if they are pretty much geometrically, materially the same, if they touch and separate, well, charges move really quick. And so when they touch and separate, these are actually going to separate out. So if originally you had some amount of charge minus Q, now you're going to actually have minus Q over 2 and minus Q over 2 because that charge is going to be evenly split. Something else to keep in mind is that even if we don't have objects exactly in direct contact, we can still have what is known as an electrical discharge. So for instance, if I bring this positive one close, and they're really, really close, if there's enough of a charge imbalance and the separation distance is small enough, we might literally get electrons to spark over and come to this other one. That is an electrical discharge. It's pretty much like a tiny little lightning bolt that's going to carry the charges from one object to another because they're able to overcome the insulating effects of the air. But let's imagine that we had a conducting sphere and it's negatively charged, and we bring it near this neutral one, but they don't touch. Well, if they don't touch, all the positive charges on this neutral sphere are going to be moved to the side near the negatively charged sphere, and negatives are going to move away. And that's just a result of how charges interact with each other, where the positive charges are attracted and the negative charges are repelled. But then if we separate them back out, these positive and negatives are going to mix up again, and we're going to have a nice zero charge that's been consistent. It's never gained or lost any charges. And this is a process known as polarization. Polarization is just a separation of electric charge within an object. It is not charging the object. It's not gaining or losing charge. It's just separating it into positive and negative. And this is always going to result in an attraction between the charged and neutral object because we have an attraction here and a repulsion there. But Coulomb's law tells us when charges are closer together, they have a much greater force than if they're farther away. So these positive charges are going to have a much bigger electric force with the negatives, and these negatives will be a much smaller force because they're further apart. So it will always result in a net attraction. Now the same thing can actually happen with an insulator. Now if I bring this negatively charged object near the balloon, now the molecules of the balloon, you've got your nuclei with the electrons going in little orbitals around them, but when we bring this negatively charged object nearby, well, the electrons can't move all the way to the other side of the balloon, but what they can do is we will actually get these stretching of the molecules, and they will actually form what are known as electric dipoles, where we get the positive nuclei on the left, closer to the negatives, and the electrons, while they don't go away, will stay on, for the most part, on the right side of the atoms, and this will still result in a net positive attraction. It won't be as great as for the metal, but it will still occur, and then when we separate it back out, it goes back to just the way it was. But this process of polarization actually gives us a third way to transfer charge, which is charging by induction. Now this is a multi-step process that takes advantage of inducing polarization within an object. That's why it is induction. You're inducing this charge on different sides of the object. So let's say we originally have two sets of spheres, and these are both just neutrally charged, no charge between them. We're going to look at two different scenarios. One where a negative balloon is brought nearby, and one where a positively charged balloon is brought nearby. Now for both of these, that's going to automatically polarize the conductor that is nearby, and the opposite charges will be attracted. They'll come to the same side. The like charges will move away to the opposite side. And this will actually even induce some polarization in the second sphere, though it won't be quite as severe as in the first sphere. So we bring a charged object near a neutral object, thereby polarizing it. Now, we touch the two spheres together. And when we touch them, well, this is a conducting path, so all of the electrons move over here to this other sphere because they want to get as far away from the balloon as possible. And same thing in the bomb situation, all the negative charges move to the nearby sphere because they want to get near the positive charges of the balloon. So we touch the second neutral object to the polarized object, and that allows those electrons now to move between. And now we separate the two objects. And when we separate the two, well, now we have all negatives trapped over here, positives trapped over here, or on the flip side, negatives trapped over here and positives attracted over here. Now this is really, really crucial. We separated the object before we removed the balloon. Because if we had removed the balloon and we'd gone realist, like go back to this previous situation, if I had moved the balloon away, well then the charges would just rebalance themselves and they would go back to being electrically neutral. So we have to separate them before getting rid of the charged object. But there's another way you could have gone about doing this that is pretty much exactly the same. There's just one small tweak that basically now I only have one conducting sphere in either situation. I bring the charged balloon nearby, polarizing the neutral sphere in one way or the other. Now rather than touching a second sphere to this, what you can do is literally, just with your own body, touch it yourself. Now when you do this, well in this top situation, when we touch it ourselves, all the electrons that were on the sphere want to get away from the balloon, they travel down through our body to the ground. And on the opposite side of things, if we touch it when there's a positive balloon nearby, a bunch of negative charges from the ground will come up through our body and go to the sphere because they are attracted to these positive charges. So they're going to go this way. And this is a process known as grounding. To ground an object is to connect it to a very large object that contains a surplus of positive and negative charges. Now, we do contain such a surplus, but not a humongous amount. But typically speaking, we're pretty much touching the ground. So as long as we are fairly easily connected to the ground, so as long as you're not wearing, I don't know, platform shoes or staying on a chair or something, if you touch this sphere, you are close enough that those charges are going to go from the Earth to the sphere or back in the other direction. And then from here, we just move our hand away, we can remove the balloon, and voila, we have once again charged an object by induction. So what are the main takeaways for this lesson on charge transfer? One, can we apply the law of conservation of charge to analyze how charge can be redistributed, at least on an object or between objects? Can we explain 3 different methods of charge transfer, whether that is the triboelectric effect, the rubbing, conduction, or induction? And can we explain the concept of polarization, which very much ties into induction? And can we predict how charge will be redistributed on conductors and insulators in many of these different scenarios?